Ladies and gentlemen, my name is Tuan Vodin, Director of the Fitzpatrick Institute for Photonics at Duke University. With pride and honor, our institute will partake in the momentous grand celebration marking the 100th anniversary of Duke University. We are thrilled to contribute to this historic occasion by hosting today's special symposium, The Light in Service of Society. This symposium showcases our institute's dedication to advancing innovation and knowledge in photonics, which is the science of generating, controlling, detecting light. Today's special event highlights the multifaceted dimension of Duke research endeavors, spanning across decades and elucidating the profound impact of light-based research on society. Without further ado, it is my distinct honor to introduce the President of Duke University, Dr. Vincent Price, who will present the opening address of the Centennial Celebration of Duke at our institute.
As President of Duke University, I am delighted to welcome you to the Centennial Symposium on Engineering Light to Empower the World. As part of this symposium, hosted by Duke's Fitzpatrick Institute for Photonics, you'll have an opportunity to learn about groundbreaking faculty research and innovations in light-based technologies. You'll also be able to explore the many applications of light in both research and everyday life, and enjoy a special session celebrating the beauty of light in art and photography. Again, welcome to what is sure to be an exciting and enlightening symposium.
It is my pleasure to introduce the Dean of the Pratt School of Engineering, Duke University, Dr. Jerome Lynch, who will present the opening remarks on the Centennial Celebration of Duke at our institute.
Welcome to the Centennial Symposium on Light in Service of Society. I am Jerry Lynch, the Vinnick Dean of Engineering here at Duke University, and I could not be prouder to celebrate the Centennial Symposium with you. Light is one of the most basic forms of transmitting energy and an essential ingredient to maintaining the very existence of our society. I was recently struck by how captivated our community was by the lunar eclipse that occurred in many parts of North America. It was amazing to see the public turn out to watch this awe-inspiring and historic cosmic event. It reminded me of how integrated humans are to the sun. It is this existential partnership between humans and light that is bedrock to the human ingenuity that has harnessed light to advance the common good. Some applications empowered by light include the development of modern wireless communications, also included the use of light-based technologies for healthcare applications, including laser surgery and medical imaging. As Duke turns 100 years old this year, we could not be more excited to celebrate Duke's role in the development of light-based technology for the common good. Our Fitzpatrick Institute of Photonics, established 25 years ago, is home to the multidisciplinary Duke community that is committed to advancing photonics research and education for broad societal impact. The lightning talks associated with this Centennial Symposium on Light feature just a small number of the many exciting photonic innovations ongoing here at Duke. From the work of Dr. Natalia Lischnitzer in the development of metamaterials that manipulate light at the nanoscale, to the work of Dr. Cynthia Tooth and the late Dr. Joe Izat in the development of optical coherence tomography to guide surgeons during operations of the eye. One cannot help but be inspired. The work you will see also offers a glimpse into the future of photonics. As our community begins to turn its gaze out toward Duke's second century, I know it will be the Fitzpatrick Institute that will be illuminating the path forward in translating our groundbreaking work in photonics to better the human condition. So, on behalf of the entire Pratt School of Engineering, thank you to the members of the Fitzpatrick Institute Photonics community for your ingenuity and broad societal impact. Go Duke!
The Centennial Symposium on Light in Service of Society stands as a crowning event of our celebration, underlining the essence of Duke University's century-long commitment to pioneering research and societal impact. As we gather to commemorate this significant milestone, we are not just reflecting on the past, but also looking forward to the future, guided by the illuminating beacon of light-based technologies and the transformation potential. At the heart of the Centennial Symposium is a series of video presentations from Duke University, crafted to showcase the rich tapestry of Duke's contribution to photonics research. Each presentation serves as a tribute to the pursuit of knowledge and innovation that underlines the university's role in shaping scientific discovery and technological innovation in the realm of light-based sciences. Now I would like to introduce the next presentation from Dr. John Dudley, Chair of the UNESCO Committee of the International Day of Light. Dr. Dudley's address pays tribute to the legacy of exceptional individuals like Dr. Charles Towns, a distinguished Duke alumnus whose groundbreaking discovery of the laser process reverberates through scientific history.
It's a great pleasure for me to deliver this message to the Fitzpatrick Institute of Photonics Symposium 2024. My name is John Dudley, and I'm the chair of the steering committee of the International Day of Light, an annual celebration of the United Nations organization UNESCO, whose aim is to promote the many ways in which light science and technology together work to improve society and quality of life worldwide. The Fitzpatrick Institute of Photonics has been a founding supporter of the International Day of Light since it was first proclaimed. And the events that you've organized have been inspiring students and the public for many years. Of course, the outstanding research at the Fitzpatrick Institute of Photonics has also contributed in major ways to meeting the ambitious goals of UNESCO in applying science and technology to achieving sustainable development in areas of healthcare, environment, communications, and so on. Now, this year in 2024, there's a very special reason to celebrate because this is the centennial anniversary of Duke University. Over 100 years, Duke has been a training ground for many brilliant minds who have left indelible marks on our world. Amongst these illustrious alumni, we have to mention Charles Towns, a name synonymous with the development of the laser, for which he won the Nobel Prize in 1964. But it was at Duke in 1937 that he began his research career with his master's dissertation. And it was this experience at Duke which set the scene for his subsequent career. Charles Towns is an inspiring figure and an example in so many ways. Not only did he develop the laser, which revolutionized multiple areas of science and technology, he also argued with great commitment for continued support of basic research, and he provided great service to the community, both the community of science and society at large. Celebrations such as the International Day of Light and events such as the Fitzpatrick Institute of Photonics Symposium are ideal occasions for us all to reflect on the ways in which science and society interact and how we ourselves can work together to make a difference. I wish you all the very best for this symposium and my sincere congratulations to Duke University on the occasion of its centennial. Thank you very much.
Hello, I'm Professor Nan Jokerst of Duke University. Now, before we jump into our nanotechnology exploration, let's first talk about what we mean when we say nanotechnology. First, what does the word nano mean? And did I change my name to Nan when I took this job? Well, for the first question, nano means 1/billionth. So a nanometer is 1/billionth of a meter. And as to the second question, no, my parents chose that name without intuition of my future profession. But I did end up rather small in size, so it all worked out for the best. This scale bar gives you an idea of the size of different objects in our world. First, at the right side of the scale bar is the 1 meter mark. At this size we have, for example, a human. The average adult human is about 1.5 meters tall on the short side, that's me, to nearly 2 meters tall on the tall side. Now let's move to the left along the scale bar and consider smaller objects. A mobile phone is about 0.12 meters long or 12 centimeters long. Continuing on to smaller objects are insects such as ants. These ants are about 2 millimeters long. So we're now at the millimeter scale, or 1/1000th of a meter. Continuing on to the left on the scale bar are even smaller objects. We have a human hair, for example, as seen under an optical or light microscope. The width of the human hair is 0.1 millimeters or 100 micrometers. In the lingo of the nano world, we call micrometers microns. Now we see bacteria here, such as E. coli, are even smaller. These bacteria have been imaged with an electron microscope, and the bacteria are about 2 microns in length. So an E. coli bacteria are about 1 million times smaller than a human. But hold on, viruses and DNA are much smaller than bacteria. So our next object here is a reconstructed image of a virus. This just isn't any old virus either. This is the rhinovirus, which is the cause of the common cold. The width of a rhinovirus is a mere 30 nanometers. That's 0.03 micrometers, which is nearly 10,000 times smaller than the diameter of a human hair. At the far left side of our scale bar, we have a DNA molecule with its characteristic helical shape. The width of the DNA helix is about 2 nanometers, which is about 1 billion times smaller than the height of a human. So back to our first question, nano, meaning 1 billionth, describes feature sizes that are about 100 nanometers and smaller, which is this left side of the scale bar. Just for fun, let's go in the other direction on our scale bar and see how big an object would be if it were not 1 billion times smaller than a human, but rather 1 billion times larger than a human. The diameter of the sun in our solar system is about 1 billion times larger than a human. That's pretty big. So the comparison between a human and DNA at the nanoscale is the same as comparing the size of the sun to us. Technology at the nanoscale is a diverse field that's part of our everyday lives, often in ways we don't realize. Nanotechnology is used in many industries. For example, consumer electronics such as laptops and mobile phones. Some fabrics use nanotechnology for stain-repellent coatings. Nanomaterials are also used in cosmetics and in construction or composites for abrasives, and in sports for high-strength, lightweight equipment. The automotive industry uses nanotechnology for structural materials and electronics, such as fuel cells and batteries. Nanomaterials are also used in applications to deliver chemicals or to filter fluids. For example, carbon nanotube-based water filters not only remove bacteria, viruses, and other contaminants from drinking water, but also they may end up being less expensive than other methods for water filtration, which is particularly important for developing regions of the world. Medical research is exploring the use of nanoparticles to deliver medications to the site of a tumor. And nanoparticles and quantum dots are being used to treat antibiotic-resistant bacteria. Nanotechnology is an enormous field that studies small feature sizes with broad applications.
My name is Rourke Horstmeyer, and I lead the Computational Optics Lab at Duke University. Our lab develops new microscopes, cameras, and computer algorithms for a wide range of applications, from forming 3D reconstructions of organisms that are freely moving, to detecting the presence of cancer within histological images of tissue. Our work really lies at the intersection of optics, signal processing, machine learning, and biology. And given the interdisciplinary nature of what we work on, we are really very happy to be a part of the Fitzpatrick Institute of Photonics. High-resolution imaging really lies at the center of many different research efforts. So we collaborate with a lot of different labs, both at Duke and other institutions, to help other researchers and other clinicians capture the most useful and informative image data that they possibly can for their experiments. Looking forward to the future, I think imaging really lies at the core of a lot of research disciplines, and coupled with new machine learning and artificial intelligence methods, these imaging tools are going to become increasingly useful and powerful, and we are excited to be a part of that research effort.
Hi, my name is Ameya. I'm a PhD student at the Computational Optics Lab at Duke. In the Computational Optics Lab, we work on camera array systems that allow us to look at very small objects over a very large area. And this technology has many, many applications, but the one that I find most exciting is in the hospital. Doctors use a technique called cytopathology to diagnose many types of cancers. In this process, doctors use a very small needle to draw cell samples from the suspected tumors. And then these cell samples are then smeared on a glass slide. Doctors use a very high power microscope lens to search for signs of cancer. Now, as it is a very high power lens, it can see in a lot of detail, but it cannot see a large area. To solve this problem, our lab has created a camera array scanner, which can look at a very large area in a single snapshot, and therefore it can digitize entire cytology smears in 3 dimensions under 5 minutes, which is at least 4 times faster than any other method currently available. This also allows us to use machine learning and AI to provide valuable insights for cancer diagnosis to the doctors and save a lot of time required for the diagnosis.
Hi, my name is Melissa. I'm a second-year PhD student in the Computational Optics Lab working under Dr. Rohrhorstmeyer. I work on a technology called diffuse correlation spectroscopy, or DCS. DCS is an optical technology used to measure blood flow non-invasively. In DCS, a laser is used to deliver light to the surface of the scalp, and some of this light will scatter down to the brain tissue and scatter back outward. And when we measure the backscattered light a few centimeters away, we're able to observe a laser speckle pattern. The time-varying statistics of this laser speckle pattern is used to then recover tissue blood flow. However, DCS suffers from one major limitation, which is the inherent trade-off between brain sensitivity and signal-to-noise ratio. In our lab, we're taking advantage of new single-photon detection technology to provide a solution for this. We use parallelized detection detectors, which allows thousands of detectors on a single compact chip to sample much more light than possible. We then average the blood flow measurements from all of these individual detectors and produce measurements with very high signal-to-noise ratio and high brain sensitivity.
Hi, I'm Lucas, and I'm a postdoctoral researcher at the Computational Optics Lab. As you probably know, microscopes are really great to magnify tiny biological samples like cells, for instance, these human neurons here. And although this works really well, it is often difficult to make out the different parts of the cells or to distinguish the cells from the background even. We say the contrast of these images is low. One way to enhance the contrast is to use artificial antibody markers that biochemically bind to certain components of the cells and then show up in the image. For instance, nuclei or cell body or exome stains. You can overlap them and that looks pretty cool, but these stains are usually expensive, the process is very time consuming, and they can even interact or change how the cell reacts to certain conditions. Here at the Computational Optics Lab, we work on digital staining. This works by taking normal label-free images and then using an artificial intelligence, a neural network, to predict images that look as if they were actually stained with an actual biochemical stain. But it's all done computationally in the post-processing. If you want to know more about this research, you can find a nice summary paper here or our YouTube link of this lab here.
Hi, my name is Kevin Welsher. I'm an associate professor in the Department of Chemistry. And I want to tell you a little bit today about the efforts that we've been making to lock on to single molecules and viruses in solution. Now, across science and medicine, we think a lot about how we actually measure molecules. And for many purposes, this can be thought of as a fairly simple process. If we have a sample that contains molecules, maybe if they're fluorescent, we can insert them into a sample holder, and we can illuminate them with light, and then collect light that comes out. This is basically the process of spectroscopy. When we do this, we get an average measurement of all the molecules in solution. But if we take a closer look, if we zoom in on what these solutions actually can contain, it's millions upon millions upon millions of individual molecules, each in unique states and with unique dynamics. So when we make a measurement in the bulk, we actually make an average of all these molecular subpopulations, and it can obscure critical groups that might be responsible for critical dynamics. Now, there are ways that we can isolate measurements on single molecules. If we're able to focus a laser beam into our solution and wait for a molecule to diffuse through, we can actually isolate the properties of that individual molecule. So these types of measurements on individual molecules will allow us to reveal how individual molecules behave in terms of their structure and dynamics. Now, this process is a little more complicated than it seems because molecules are not static objects. They are dynamic. They change state, much as this little cartoon of a protein is doing in this animation, flashing different colors as it changes state. As it does, it diffuses. It moves through its environment at very high speeds. So the amount of time it spends within our observation volume is very short, and the amount of information we get out as a result is also very small. So one thing we think about a lot is how do we capture the dynamics of single molecules in solution? How do we overcome this very small dwell time within our observation volume? Now, luckily, there are a lot of real-world analogies that can help us try to figure out this scientific problem. And we call these under a subset of target-locked observation. One inspiration is the high-speed chase, where a helicopter with a camera can actually follow a car through traffic. If we think of this as our molecule, we can see it interacting with other molecules because we are locked onto its position as it moves through a complex system. We want to apply this same idea to our molecular environment. Similarly, in video games, we do the same thing. We can capture fast dynamics of what Sonic is doing here because we are constantly locked on his position. So we can capture the dynamics of the character in our video game or the driver in our high-speed chase simply because we are constantly locked onto their position. So that's what we do in our lab, is we try to develop methods that can lock onto the position of molecules in real time so that we can constantly observe them regardless of where they are within an environment. Briefly, how we do that is we scan a laser beam at very high speeds in 3 dimensions. So you can see two parts of the scan here. One is a Knight's Tour scan, where we scan roughly in little Knight steps around a small grid in XY. We do the same thing in Z. So basically, we have a 3D laser scan. And whenever our laser spot overlaps with a molecule or a virus, and if that molecule or virus is fluorescently labeled, we get a burst of photons. We get light. And when we get that light, it tells us something about the real-time 3D position of that object. And then we use a 3D high-speed nanopositioner to lock onto that object. To go back to the analogy of the high-speed chase, this laser scan is like the camera on our helicopter, and the high-speed nanopositioner is like the helicopter moving to follow our object in solution. So what does this look like? What happens when we enact this type of measurement on molecules in solution? It looks something like this. On the left-hand side of the screen, I'm showing you active feedback tracking or real-time tracking. We call it 3D single molecule active real-time tracking, or 3D SMART, of 100 nanometer fluorescent nanoparticles diffusing in solution. The camera screen in the middle is showing you the locked, freely diffusing nanoparticle that we are following at high speed. It appears to be stationary just because we are following it at high speed, much like the helicopter follows the car in the high-speed chase, or we follow Sonic within our video game console. On the right shows the scalability of this process. We can actually do this process on anything that is fluorescent. So on the right is a 3-dimensional trajectory of just one molecule diffusing in glycerol solution. So as long as we have something that is fluorescent, we can lock onto its position and continuously monitor it with high spatial and temporal resolution wherever it goes in solution. So this gives us a unique opportunity to study things such as viruses. And we are very interested in how viral particles make very first contacts with tissue and cells. So in very broad strokes, we can think of a virus as a diffusing object in the extracellular space. Here I'm showing you a cartoon of a virus landing on the cell surface, maybe eventually interacting with a receptor and infecting this cell. Now, this is a very kind of isolated picture when the reality is much more complicated. The extracellular space, luckily for us, is full of immune defenses. We have mucus, we have an epithelial layer that all protect us from viral infection. And we've been using this type of target-locked observation, this active feedback microscopy, to track the early stages of interaction of viral particles with the cell surface. So here's an example of a fluorescently labeled viral particle. What we do is we actually take fluorescent proteins and fuse them with viral proteins and then developed virus-like particles that we can track throughout the infectious process. So here we use lentiviral particles, which are part of the same family that HIV is a part of. And we put green fluorescent protein inside the capsid. And on the left is the result. We can actually track single viral particles. This is showing a trajectory of one viral particle in real time. So you can see it kind of diffusing around in our little tracking spot. But we can get very rich information on the dynamics of these viruses in solution. Now, on its own, this gives us some information about the viral particle itself. But what we really want to know about is where do these viruses go, where do they infect, and how do they do it? And to do so, we integrate with our active feedback tracking microscope a 3D imaging microscope so that we can actually follow the dynamics of a single viral particle in cellular context. So briefly, what I'm showing you here in real time, again, this is the real-time motion of this viral particle, is a fluorescent viral particle. That's the path you see in green. And all these large structures that are yellow and purple are actually live cells. The yellow is the nucleus, the purple is the extent of the cytosol. So what we're seeing here is all the transient millisecond scale contacts that this one viral particle is making on the cell surface before it eventually goes on to infect the cell. So in our lab, we're very interested in taking this all the way from individual cell cultures to tissue models so that we can see how viruses eventually make their way through our epithelial and our mucosal defenses. So with that, I'd like to thank all the people in the lab who do this very hard work. And like we like to say, we're all just a bunch of microscope dorks.
Hello, my name is Natalia Lichnitzer, and I'm a professor in the Department of Electrical and Computer Engineering here at Duke with the secondary appointments in MEMS and physics. Today, I would like to highlight some of our research on light and darkness in nanomaterials. First, let me introduce our nanophotonics and nonlinear optics group. We have a wonderful team consisting of undergraduate students, graduate students, and postdocs. And we work on the intersection of so-called structured light, nanomaterials, and nonlinear optical materials. And of course, we're always grateful to our sponsors. So what is structured light? It is light modulated or shaped in space and time. It can carry spin and orbital angular momentum that can be visualized like in the cartoon picture below. So imagine the Earth rotating around its own axis. This is what we call spin. Now we know that the Earth also rotates on the orbit around the Sun, and this is what we call an orbital angular momentum, which we abbreviate as SAM and OAM. Now, can we manipulate shape, spin, and orbital angular momentum of light? With nanostructures or nanomaterials, indeed we can. And we can do it on the very small or nano scale. What are those materials? They are engineered man-made structures that may realize properties that cannot be found in natural materials. And what's more, we can integrate those artificially created unique structures with conventional optical fibers that are used in telecommunications or in, for example, medical endoscopy. So now I want to convince you that what we call structured light is not something abstract or technical that you have never seen before. In fact, you do see structured light around you pretty often. And next time you have a cup of coffee or swim in a pool, look at this kind of patterns shown on the left. And these are optical singularities that form when several light waves combine together or interfere with one another. Singularities are responsible for the dark core of the beams that I'm showing here and we discussed on the previous slide. And at this point, the intensity of light vanishes and the phase or phase front twists around this dark spot, much like a tornado. Singularities can even twist in all three-dimensional space and then form what is called an optical knot, much like knots that we tie on our shoes, except it's optical. So why do we physicists and optical engineers care about knots? Well, this great student and a postdoc, a student in my group, investigate if we can improve optical communication through the atmospheric turbulence, where conventional light beams fall apart. Or can we use optical knots to actually probe how severe the turbulence is? So that's what we hope to accomplish with optical knots and use them as a new carriers of optical information. So how do we shape light into the knot? Well, we use these super thin structures called metasurfaces to shape light in any kind of three-dimensional complex structure. Notice that the thickness of this, what we call metasurface, is only around 300 nanometers. For comparison, a human hair is about 100 microns, so orders of magnitude thicker. So since we just talked about metamaterials or metasurfaces, let me mention another fascinating project that our postdoc is working on in collaboration with my good collaborator and colleague at University of Massachusetts Lowell, and with also support from Intel. Here, we make metastructures that can significantly improve Intel's capability to visualize, characterize, and improve their chips. And the structures that we're designing here called hypergradings and tandem hyperlenses. So moreover, we further develop the so-called hyperbolic structures, hypergradings, hyperlenses, to focus light to deep subwavelength scales. So that's what I'm showing here. We start with just simple light beam looking like a tornado or optical vortex, and we want to squeeze it to deep subwavelength scales, which means just say 50 nanometers or less. So why is this important? First, the ability to squeeze structured light to the nanometer scale offers unprecedented opportunities for the spectroscopy of so-called dark or forbidden electronic transitions. Why structured light is needed here? Well, because spin and orbital angular momenta can add up to excite the electronic transitions otherwise prohibited by the fundamental selection rules. In addition, here we discovered while doing this research something called optical skyrmion. So this is a structure looking like that. And so this is pretty much the structure of electric field, which is distributed such that it forms this deep and maxima on really deep subwavelength scales, on a scale of just a couple of nanometers. And that opens even more opportunities for really few nanometer scale imaging. So Our other super exciting relatively new project is done in collaboration with the School of Medicine and specifically with Professor Gerald Grant, who is the professor and chair in neurosurgery. And this project is focused on designing advanced real-time imaging capabilities that would improve the quality of imaging that neurosurgeons need. And finally, you may ask how the design this advanced metamaterials or metastructures is actually done. Well, of course, we start with our basic understanding of physics and our intuition based on fundamental physics laws and principles. However, sometimes our intuition is limited to simple and regular geometrical shapes such as cubes or cylinders or spheres. And those shapes is what we use to create metasurfaces or metamaterials, and we call them meta-atoms. So, well, how do we do something better than those simple geometrical shapes? Well, that's where machine learning helps us. And so we developed several models, forward, inverse model, and electric field prediction models that help us perform several design tasks, such as, for example, we want some physical properties, some response, for example, strong field enhancement at certain wavelengths. Then we basically ask our model to suggest a shape that would provide this particular response. And recently, we actually proved that our physics-backed so-called machine learning models indeed work. So here in this experiment, we actually validated our results predicted by machine learning model and made a metasurface out of material called titanium dioxide, which is nice and transparent in the visible wavelength range, and as well as at even shorter wavelengths in the UV. So this was first demonstration that our machine learning models indeed give us new functionalities that we will in the future use in many projects, including underwater communications. And with that, I would like to thank you for your attention.
Happy birthday, Duke. My name is Junjie Yao. I'm an associate professor of biomedical engineering at Duke University. I'm going to talk about our technologies on photoacoustic imaging and how this technology can help us with basic science and clinical management of disease. So first, I want to thank my lab members and also my wonderful collaborators at Duke and across. And in photoacoustic imaging, what we do is we shine light into the tissue with a very short laser pulse, and then the light is absorbed by the biomolecules in the tissue, which generate ultrasound waves, and then we can detect ultrasound waves outside the tissue, and then we can form an image of the biomolecules. So in photoacoustic imaging, we really have two parts. The first part is optical excitation. The second part is ultrasound detection. So in the first part, we can have optical contrast. So we detect the biomolecules based on their optical absorption. In the second part, we use ultrasound detection, so we can go deeper than traditional optical imaging. If you put photoacoustic imaging into the context of other optical imaging modalities such as confocal or two-photon microscopy, actually we benefit from the better penetration depths into tissue with a higher resolution. And in photoacoustic imaging lab at Duke, PyLab, and we develop a wide range of technologies around photoacoustic imaging. And using those technologies, we can contribute to the basic science, help us to understand more about how the nature works, and also help us to make a better diagnosis of disease, for example, stroke. And then it also helps us to treat disease with better efficiency and more accuracy. And so all those technologies are used for different purposes. I'm going to give you just a few examples of what we can do with those technologies and how they contribute to the science and clinical management. disease. So the first example is actually quite relevant to us. It's a drug response study. So we use photocosmology to look at how epinephrine, a widely used drug to treat cardiac patients, and how does the brain respond to this drug. And this video can show that once we inject the drug into the mouth, the brain becomes really hypoxic, meaning that there's a lack of oxygen in the brain, which is not good, right? So it basically gives the brain not enough oxygen to survive. So this will cause bad consequence to the brain tissues, which may actually give the the patient with a side effect after the drug injection. So this has been highlighted by a major journal in the medical field, so we can say that this may generate a long-lasting impact on how the patients are treated with epinephrine, especially for cardiac arrest patients. The second example is how we can use technology to discover how a very magical animal to become or to keep safe. And this is the glass frog we got from South America, and we are really puzzled by how they can become transparent when they're sleeping. So we cannot, as humans, we cannot become transparent, but these frogs can become transparent. So how do they do that? So we use photocosmology technologies to study this, and we find out, wow, those magical creatures, they can concentrate their red blood cells into the liver region without losing their health. So basically they can remove the red blood cells from their vessels and just hide those red blood cells in their liver, 90% of them. So they can live without red blood cells almost for 10 hours a day, every day. So by doing this, they can become much more transparent, and which is actually beneficial for them to stay away from their predators such as birds, so they keep safe. And if you look at how they can become transparent when they are falling asleep, by photocosmology you can say gradually or quickly they actually move the red blood cells from the blood circulation system so they become more transparent. So last example I'm going to give you is how we can use photocosmology to study pregnancy. So placenta, we know that is vital for pregnancy because it transports the nutrients, oxygen, and other very important molecules from the mother to the embryo. But it's very challenging to study placenta because it's so deep inside the body, and also it's constantly moving. So we have developed a photocosmology technology that can monitor the placenta development over the entire pregnancy without causing trouble to the placenta or the embryo. So now we can image those placentas while they are growing from the day one to the last day of the pregnancy in the mouse model, which is about 20 days. So you can see they grow up really quickly, and they also do drastic vessel remodeling, meaning that they're changing their vessels almost every day, and to prepare for the embryo development and also to prepare for the delivery. So what is the application? And we can study, for example, how alcohol consumption changes the placenta microenvironment. Well, know that the alcohol is not recommended for during pregnancy. However, this is the first time we're able to look at the placenta down to the macrovessel level and see how they can how they respond to alcohol consumption. So this is a video showing once the alcohol is consumed, there's a huge increase in the oxygenation level and also blood perfusion and vessel dilation. It happens very quickly inside the placenta, which is actually not good because the placenta itself prefers to have a pretty low oxygen level in order to keep healthy. So this kind of high perfusion and high oxygenation level is actually not a good thing for the placenta development. So overall, I think we have a wide range of technologies we develop in the lab, and we're using those technologies to contribute to basic science, new knowledge, and we try to use those to bring us more power and flexibility and accuracy in terms of disease diagnosis and treatment. And everybody's welcome to visit us. We're at Hudson Hall Annex, and feel free to drop by. And again, happy birthday, Duke.
Ladies and gentlemen, the next stop is very special as it reflects the legacy of a pioneer in photonics and a remarkable individual, Dr. Joseph Isaac. It is with heavy hearts that we bid farewell recently to Dr. Isaac, whose lifelong contribution to the field of optical coherence tomography have left an indelible mark on the landscape of medical science. We are fortunate to present here a video recording from Dr. Isaac, who discussed his research and the new frontiers of the important area of medical imaging of the eye.
Hello, I am Joseph Isaac. I am a professor of biomedical engineering and chair of the Department of Biomedical Engineering at Duke University, also a professor of ophthalmology, and I'm very pleased to present this lightning presentation on new frontiers in optical imaging of the eye. For more than 20 years, my research group and I have collaborated with various collaborators at the Medical Center and in engineering at Duke to develop new instruments for imaging of the human eye. The human eye, as illustrated here, is oriented very much like a camera. It has a lens at the front. We can image the lens with several technologies, such as illustrated on the left-hand side of this slide, and it has a detector at the back called the retina, which receives light from the front of the eye, forms images, and sends those images to the brain. We also have various technologies for imaging the retina of the eye. I'm pleased to have collaborated with surgeons such as Dr. Cynthia Toth, Dr. Anthony Kuo, and Leila Vajovic, as illustrated here, as well as other engineering collaborators at Duke University. One of the principal techniques nowadays for imaging in the eye is called optical coherence tomography, or OCT. OCT was invented over 20 years ago and has since become the principal means for diagnosing serious retinal and anterior eye diseases of the eye. OCT has gone through several technology iterations over these 20 years, and our group at Duke has played a leading role in developing and introducing many of them. In particular, over the past 10 years or so, we've been very interested in taking OCT from its current setting of being used primarily in ophthalmic clinics for examining patients to interactive applications where ophthalmologists and surgeons can take OCT out of the clinic and use it either in examination situations such as handheld probes for imaging of infants and babies and children, illustrated here, as well as into the operating room for actually imaging during surgery, during live human surgery, and that's illustrated here. Both of these handheld and intrasurgical OCT systems, as developed by our team here at Duke, have been investigated thoroughly in clinical investigations, which we publish in journals, as well as commercialized through two startup companies, Bioptogen, which was acquired by Leica in 2015, and Thea Imaging, which specializes now in imaging of infants and children. Exciting work coming out of our work with OCT has been in intrasurgical imaging using newest technology which enables real-time volumetric imaging for the first time using this technology. This makes OCT one of the highest throughput medical imaging technologies in existence. It's faster than MRI or CT or other real-time imaging technologies. And as you can see here, this enables the surgeon, while they're operating on the eye, to visualize in intricate detail and in full three-dimensional user manipulatable views the interaction of their surgical tools with the tissue. This is illustrated in the top left with a surgical manipulator, in the top right with injecting of special drug vectors into the eye, in the bottom left with manipulation of injury to the surface of the retina, and in the bottom right with actual imaging of corneal transplants while they're occurring. We've also pushed the technology very far towards autonomous or robotically aligned OCT so that OCT can be taken even further out of the ophthalmic clinic and deployed in situations where special technologists, technicians, or even ophthalmologists are not available, such as for screening applications. We've taught robots how to recognize the patient, follow the patient around, lock in on their eye, image through their pupil, and obtain retinal images even of freestanding patients who are not necessarily cooperative with the robot. This final stage in what we have been thinking of as a real convergence of technologies for a surgical revolution, starting with real-time volumetric imaging of the eye, moving towards immersive 3D visualization using techniques such as augmented and virtual reality, and finally ending in
Hi, thank you for allowing me to present today at the 2024 FIP Symposium. I will talk about the optical coherence tomography revolution at Duke, using light in a new way to guide surgeons. I'm a professor of ophthalmology. I'm also a professor of biomedical engineering and have had the opportunity to collaborate with people in engineering, particularly Joe Izat, over the past 20 plus years. In the early 2000s, OCT, optical coherence tomography, was restricted to tabletop systems, so we could access it in clinic. And we were some of the innovators using OCT in 2000 to image patients before surgery and then after surgery. But we had a black box during surgery where we would go in, perform an operation, but our view was the conventional, what I call Helmholtz view, of light going through the pupil and reflecting back to our eyes so we could see what's going on in the microscope. Why bring OCT to surgery? Well, the surgical microscope has limited depth perception and field of view, limited data on depth and location, a fixed visual perspective, and it constrains us looking through those oculars. 3D heads-up display has come on since we've been working in OCT, and although it augments stereopsis, it provides digital manipulation, which allows us to use camera gain to lower our illumination, it still has that same fixed visual perspective coming through the pupil and has problems with rapid changes in illumination and light. Depth resolved imaging within the surgical microscope by bringing OCT allows us to have much like a street view does on a map. The left is the surface, is the top view, that orange view through the microscope, and to the right is literally a street view we can extract from OCT in real time while we work. This is based on technology that Joe Izat brought to Duke in 2001. Before he came to Duke, he'd already developed portable OCT systems such as this handheld one shown here, and he developed the first tabletop system that I was able to use for the AREDS ancillary OCT study. This study started in the mid-2000s, and the use of our data from hundreds of patients has been used by ourselves, people at NIH, and others working in AI. Nora Ladd here at Duke has now used this to predict risk for atrophy in patients with age-related macular degeneration. So while we were looking at the insides of drusen, small lumps of material beneath the retina in patients, we were at that time looking in infant's eyes with the ophthalmoscope. With OCT, the portable system that Joe Izat had developed, we were able to bring this to the bedside. So on the left, you'll see the armature system that his company, Bioptogen, had started. And by 2007, 2008, we had thrown away the armature. And by 2010, we were demonstrating its use in the intensive care nursery, revolutionizing our way of understanding infant disease. Joe's company, Bioptogen, Joe's system was FDA approved in 2012. We've continued to work with him and his colleagues to develop handheld devices from 2016 till now. They're compact, lighter. The speed has gone up with every iteration. And you can see the 2022 system imaging infants in intensive care as part of the baby step study, where we gather health data, infant retinal data, the conventional exam from the indirect, magnetic resonance imaging of the brain, visual acuity, And now we're gathering neurodevelopmental outcomes at age 2 years and vision in the kids at 5 years. And this is helping us understand how the low stress OCT imaging can allow us to predict outcomes in infants born premature. Because the limits of that system, actually, 2 Duke BME graduates, Christian Wieland, who had his PhD with Joe Izett, and Hafiz Dalla, have partnered with me to start a company, Thea Imaging, in downtown Durham, to make such advanced ophthalmic imaging diagnostics accessible to infants, children, and those unable to cooperate for tabletop imaging. This is an example of an investigational system that's been used in research in adults to image not only the center of vision, but out in the periphery. So now let's come back to the core work at Duke and what's been going on more recently with Joe Izett and the team. Once we got Professor Izett to Duke in 2001, he has been a boon to the advancement of all sorts of research in ophthalmology. Shi Chen, Anthony Kuo, myself, Leila Vizovic, Sina Farsu, who's a professor in BME, have all collaborated with Joe and benefited from the amazing innovation of his research team for our applications for patient care. He's helped us to shrink the black box during intraoperative procedures. OCT before surgery can show us what's going on, usually done in adults in clinic, but we still couldn't image during the procedure. We could bring the handheld device in a sterile covering and catch OCT at pauses during surgery. But that didn't help us during the operation. So to open the black box, Joe and Kenny Tao, Justice Ellers working with me, Sina Farsu, and many others helped to develop the intraoperative OCT. And that system allows us to see in 3D the images that were the landscape that we're working on with our microsurgical instruments as we work. That was commercially translated by Joe and his colleagues to Bioptage and Leica, and they developed a system with external screen that is now sold worldwide. But at the same time, Justice Ellers, who went on to Cleveland Clinic from Duke, has demonstrated that intraoperative technology impacts decision-making in clinics and in surgery. The commercial use of intraoperative OCT can be shown here with the Leica Preveo and focus system, where during peeling, the membrane on the surface of the retina can be visualized and followed. And here you can see it in a video during surgery. But note that in both cases, while OCT provided a breakthrough, the first time that we could extract depth-resolved imaging, that these are only cross-sectional views, and we don't have that 3D view, that I promised you at the beginning of my talk. And so it really was with the OCT advances and speed that the Izett lab developed that we were able to now move to street view, where the surgeon, as I go in and grasp and peel, can see in 3D and at the margin where I'm grabbing tissue and how we maneuver it in surgery. The current generation is dependent on the work of many students, several of whom were won the 2016 NVIDIA Global Impact Award. It's allowed us to bring it literally translating from BME research to the wet lab, which is the upper left corner, to the lower left where Leila Vizovic is using this in human surgical research. On the lower right, you can see the MIOCT. Sorry, I was going to show MIOCT forming blebs. I'm going to show you here depth-based colorization to help us identify surface features better during a maneuver, and transvitreal delivery by Dr. Vizovich in surgery as she's delivering gene therapies and other materials under the retina of patients with blinding eye diseases. Sina Farsu and others have helped identify, including David Lee, a postdoc now in the ISAT lab, have helped identify the exact volume of material delivered and have found that that is very different from the estimate the surgeon has. Robert Trout, working in the lab, has advanced the fusion of the OCT image to the digital microscope to allow us to view in 3D both the color information and the OCT depth information. Challenges remain, though, to capture, extract, and communicate relevant imaging data to improve surgery and inform outcomes. So we're working together. For example, I'm working with So-Ting Lai and others to create summary reports of the tissue deformation through an entire procedure. This information is valuable to surgeons and surgical companies developing tools and methods of visualizing to perform an operation. It allows us to compare the retinal deformation from instrument 1 to the retinal deformation from instrument 2. And that allows us, now that we have a record, to compare between devices, between surgeons, and between systems, and improve our outcomes in the future. I'm thankful to the many collaborations across Duke, the innovation of Duke biomedical engineers throughout my 30 years here at Duke, and their students and our lab teams. It's a phenomenal place to work.
My name is Warren Warren. My research group at Duke uses lasers to image materials in ways that produce much more information than you could get from just a camera or a normal microscope image. Much of the novelty comes from techniques we've developed over the years to control laser beams with exquisite precision. An ordinary laser produces essentially a lump of light, but our technologies sculpt the light into waveforms where the amplitude, the color, and the polarization can change in much less than a picosecond, which is a millionth of a second. That is cool and fun physics, but it isn't the end goal. The importance of our work lies in the applications. I'll talk about two of them here. First, we work with dermatologists, pathologists, and surgical oncologists to improve early diagnosis of melanoma, detecting metastatic cancer before it is visible by current clinical methods. Second, we use exactly the same laser system to non-invasively study pigments, for example in centuries-old paintings, to see degradation, understand the artist's original intent, and guide conservation. Let's start with melanoma. This is the most dangerous form of skin cancer, killing 8,000 Americans every year, largely because the cancer is often not detected until it becomes metastatic, and in cancer it's almost always the metastases that kill. Someone my age might have hundreds of small colored spots on the skin. The dermatologist's job is to use her skills to detect which ones are abnormal. The rule is always, when in doubt, cut it out. After the mole is cut out or excised, it is sliced, stained, and examined by pathology. In really severe cases, they also cut out a lymph node to see if pigmented cells have invaded the lymphatic system. After that, a stage is assigned, as is done with every other kind of cancer. If they don't detect metastases, you get sent home after a wider excision, take 2 aspirin and call me in 6 months. The problem is, about 15% of the time, you actually had metastatic cancer that the doctors did not detect. Metastatic melanoma was a death sentence 20 years ago, but huge progress has been made in treatment in the last decades, largely with drugs you see advertised on TV all the time. However, these treatments are costly, which is why you see them on TV, and have side effects. Some people die from the drugs, so you can't just give them to everyone. The consequence is that more Americans die every year after a stage 1 diagnosis, which is more common, than after a stage 4 diagnosis. Now let's talk a bit about another application. The Mona Lisa has dozens of layers of slightly colored paint on her face. Long before we really understood optics, Da Vinci understood empirically the importance of scattering and three-dimensional structure in realistic art. Matisse's Joy of Life is the painting that inspired Picasso to develop what we now call Cubism and Modernism. Note the distorted figures and the shocking colors, most notably cadmium yellow, which was new at the time. Major areas of this painting which were yellow originally are now brown or white. This degradation problem became worse with the advent of beautiful organic pigments a century and a half ago. Impressionist artists such as Van Gogh knew this, but he only sold one painting in his lifetime, and he wasn't painting for us. Here is a best guess as to a restoration, done in part by a collaborator of ours at the National Gallery of Art. Understanding this degradation, and preferably figuring out how to slow it down, are the reasons why every major painting in the world is studied with scalpels, removing cross-sections for detailed analysis. Pump probe laser microscopy addresses both of these problems. Controlled laser pulses, using only 1/10 of the average power of a laser pointer, can make normally invisible molecular processes detectable and give a very richly structured image, even if the pigment itself is boring in its color. By sorting out these mechanisms, we extract extra information. Here's an example of a conventional microscope picture of a slice from a known metastatic melanoma. The dots are all melanin, the primary pigment in tissue, and they look pretty similar. With pump probe microscopy, the story is completely different. You see, this tissue is actually very heterogeneous. It has lots of underlying structure. More importantly, and surprisingly, specific combinations of colors and delays highlight substantial differences in our images that correlate with clinical concern. That means we can find many, or maybe all, of the patients who were misdiagnosed with early-stage tumors to send them to treatments that in those cases would decrease cost, because you're treating them early, and save lives. Here's an artwork example. Most of the churchgoers of the 14th century were illiterate, but they still knew the lady in blue was the Virgin Mary. Her gown is colored with lapis lazuli, the most expensive Renaissance pigment, costlier than gold. When we image through her gown, again using much less power than a laser pointer, we see the layered structure, detect the rough grains from manual processing, and see impurities in the natural paint. We've done many other applications with both organic and inorganic pigments, usually with the goal of understanding original intent or aiding in conservation. As you've probably guessed, this is an intensely collaborative undertaking and reflects the kind of interdisciplinary challenges Duke tries hard to address. It's only possible because of an outstanding team and funding from public and private sources. Thank you for listening.
Hi, I'm Adam Wax. I'm here to tell you about research at my lab here at Duke University. I run the BIOS lab, which is the Biomedical Interferometry Optics and Spectroscopy lab, and our main goal is to use optics to detect disease at the cellular level. We have a range of projects, and I'm going to run through a few of them really quickly. First off, I would like to tell you about quantitative phase imaging. And this is a holography method that lets us learn about cells at the nanometer scale. For this application, we're trying to understand sickle cell disease. This is a terrible disease that affects about 1 in every 365 African Americans. And what happens is the cells become oddly shaped, like a sickle. What happens is they become more stiff and compact, and they end up clogging up the arteries in what's called a vaso-occlusive crisis. What we want to do is use our QPI method for measuring cells very precisely to look for changes in sickle cell disease. The way we do this is with a technique called holographic cytology. And what we do is we flow our cells through these parallel channels in a microfluidic device. And we generate lots of holograms really quickly. You can see them falling down in this video as they look like something out of the Matrix. As each cell comes by, we grab it, take an image, and then we can analyze it to determine if there's any presence of disease. And we'll do this for up to 1 million cells at a time. With QPI, we can detect sickle cell disease at the point of care. The next technique I want to tell you about is optical coherence tomography, OCT, and how we're advancing it for using at the point of care. I didn't invent OCT, it's been around for over 25 years, but it lets you see all the layers of the retina and find the earliest signs of disease. On the left here, I'm showing a normal healthy retina, and on the right, you can see a diseased retina. And with this technology, just about anybody can see the difference. The problem, if there is one, is that application has been limited by cost. Typically, these devices cost $35,000 or up to $50,000 or $60,000, meaning that only large eye centers in big cities tend to have these devices. And this can limit access. In the developing world, there are fewer of these devices. For example, in India, there are less than 1,000 devices for 1.4 billion people. It also makes it difficult to expand to new clinical areas, meaning that if you want to try this device out for something else, kind of tough to do. I'd like to show you around my lab a little bit and some of the secrets that we use to make our low-cost OCT to solve this problem.
Now we're in the Duke lab in the Department of Biomedical Engineering. We have a lot of different projects going on here, but I want to draw attention to our 3D printer. You may ask, how are we able to make our OCT so inexpensive? And the answer is using rapid prototyping technologies. Usually, a spectrometer, which is the heart of the OCT system, is a precision machined system requiring assembly of lots of parts with very high precision and tolerances. On the other hand, our patented proprietary design enables us to make a spectrometer out of a 3D printed part, which has much lower tolerances. The real advantage is that our system ends up being so much more robust. It's immune to temperature changes, mechanical shock, and can be used in a variety of settings. It's also much lighter, which enables us to produce the 4-pound system. You can see here our new form factor. It's significantly reduced. It's about the third of the size and weighs about 4 pounds. We still have the integrated PC in the top, but now instead of a full monitor, we have a touch screen. This makes it more portable and easy to operate. I'd like to show you the revised design for the handheld scanner. This is similar to our previous scanner, but contains most of the components here within the handle. You can see that it's shaped in a form factor that makes it easy to use by hand. For clinical studies, we have it mounted to this slit lamp base, which makes it easier to position. You can see this 3D printed part, which was easily made to accommodate it. In order to image a patient, you have them put their chin here on the chin rest and position their eye in front of the lens.
The last project I want to tell you about, I'm going to tell you about ALCI, which stands for Angle Resolved Low Coherence Interferometry. It's a mouthful, but the idea is that we're able to detect cancer, precancerous lesions or dysplasia, using nothing more than light. Our approach is to scatter light off the cell nucleus, and by looking at the angular scattering pattern, we can determine their size very accurately. The nuclear size can be a surrogate biomarker for precancerous change, meaning that if we can measure the size of the cell nucleus, we can determine whether this tissue is moving towards cancer. Now, there are some other ways that you might measure the cell nucleus, but none of the others can do it inside of the body and without requiring some additional contrast agents. We can also do it as a function of depth, meaning we can measure it not just at the surface, but deeper into the tissue. For this project, we paired ALCI with OCT so that we can visualize the tissue as we're doing our measurements. For this OCT project, we created a new probe made out of 3D printed parts so that it can be inserted into the esophagus and look for precancerous tissues. The combined images are pretty cool. On the top row, we can see Barrett's esophagus with low-grade dysplasia on the left and without dysplasia on the right. So normal tissue on the right and precancerous on the left. Using our ALCI measurements in the second row, we can determine the size very accurately. You can see for the precancerous tissues, we get a size of 13.1 microns, which is much larger than the 8.1 microns that we get for the normal tissues. So the summary is that ALCI can detect cancer. There's no need for a biopsy, and we've shown that it works so far in the esophagus, colon, and cervix, 3 of the sites where most cancers occur. In our current project, we're trying to see if ALCI can tell us about Alzheimer's disease. So what we're doing here is we're measuring light scattered off of the retina, and determining whether there are changes that could indicate the presence of Alzheimer's disease. Now, we've done this already in a mouse model and showed that it can see early signs of Alzheimer's disease. And we're currently working on in vivo trials, being able to do this in people to see if we can see them in humans. I'd like to finish up by thanking my team. Of course, everybody has contributed to this, but in particular, Ji Song, Ken Chu, Han Sang Park, all really contributed to the work that I've shown you today. And of course, I'd like to thank my funding. I'm funded by the National Science Foundation, the National Cancer Institute, and the National Institute of Aging, as well as the National Institute of Biomedical Imaging and Biotechnology. I'll finish up by saying that I have a startup company called Lumedica Vision, where I'm the founder and the president, and this is our way of bringing these technologies to the patients that need them. Thank you very much for listening. Have a great day.
My name is Tuan Vodin, Director of the Fitzpatrick Institute for Photonics and Professor of Biomedical Engineering and Chemistry at Duke University. I would like today to talk about the combination of nanotechnology and light to develop new tools for early detection of disease for the medicine of the future. The medicine of the future is expected to have several key features that distinguish it from traditional medical practices. It is personalized, it is predictive, and preventive. That means the detection of early disease biomarkers, such as microRNAs, is a key strategy in disease management in the medicine of the future. MicroRNAs are tiny molecular messengers inside your cells, and certain microRNAs can act like red flags, signaling that something might be going wrong in your body. So by detecting these microRNAs in tissue or blood, we might be able to catch disease such as cancer in its early stage, when it's easier to treat. So our strategy is to harness the power of light using gold nanostar. So gold nanostar are tiny particles made of gold that has only 50 nanometers diameter, which is 1,000 times smaller than the human hair diameter, which is around 50 microns. And why we use the gold nanostar? Because as you see on the right, when you have a laser shine onto the tips of the nanostar, if there's a dye or molecule closer to that tip, it will glow because the so-called lightning rod effect of the nanostar. So with that, we designed a nanosensor based on the so-called inverse molecular sentinel, which is the IMS nanoprobe. And what it is, as you see here, we will see, the nanostar, which has a goal, we have a two pieces of DNA bound to each other that stretch the dye further from the tips of nanostar. So when the dye is further from the tip, there's no signal because no lining of the effect. But if in the samples, there's a target like microRNA, it is recognized by one of the strands. So they bind together, and when they bind together, they will move out slowly out of the nanostar. And in nanostar, there remains only one single strand, and that single strand is designed to curl itself close and bring the dye close to the tip of the nanostar. And when it goes to that tip, there's a so-called lining rod effect when we have a laser shine into that, as you see. So it's very simple. You have in the sample this nanostar IMS nanoprobe, and if there's a target microRNA, remove it from nanostar, and suddenly you have a signal. So with that method, we have detected HIV. You see, different signal when the sequence are set in the samples. We can detect breast cancer. We detect the BRCA1, which is a mutation that shows predisposition to breast cancer. And then, in general, we want to look like here another example of the detection of GI. The traditional technique of GI is to go inside the GI tract, detect tissue, and then send to the pathologist for analysis that result in hours and days to take the result. This traditional diagnostic technique is invasive, time-consuming, it requires high cost and skill operator. On the hand, with the IMS nanoprobe, we just have either tissue extract or blood sample from the patient, and then we put into a system of the nanostar, and we can directly detect the clinical sample, quick result, and that serves as a point of care testing as an alternative to this pathology diagnosis. So, in general, the IMS with the nanostar allow rapid point of care measurement taken directly from patient plasma or blood. The result can be analyzed within minutes to determine cancer diagnosis. So in general, we have shown that the combination of nanotechnology and light can produce a powerful system for the medicine of the future. The advantages are early detection and prevention of disease before symptoms occur. Rapid detection of infectious disease have been demonstrated. We have detected HIV, malaria, dengue, host response to viruses such as SARS-CoV-2. We have shown that early diagnosis of various cancer by detecting biomarker directly in patient tissue and blood without sample biopsy. So in general, the main advantages are simplicity, rapidity, non-invasiveness, and very low cost for point of care and global health application in low resource setting. So with that, I would like to thank all my coworkers over the years and the funding agency for them. Thank you.